Imagine holding a simple white PVC pipe in your hands. It feels light, smooth, and ordinary. Yet that same pipe can carry clean drinking water underground for more than 50 years, while resisting rust, chemicals, and enormous pressure. Most people never think about this, but one of the most common construction products on Earth begins its life in an astonishing chain of chemistry, mining, and engineering. Think about this. Every city around you depends on millions of meters of PVC pipe hidden beneath roads, buildings, farms, and factories. You never see them, yet they quietly deliver water, protect electrical cables, and support modern civilization every second of every day. But here's what nobody tells you. The journey of a PVC pipe starts nowhere near a factory. Today, we're following every step of that incredible journey. From underground salt deposits and oil fields to giant chemical plants, high-speed extrusion lines, robotic inspection systems, and pressure testing laboratories. You'll discover how heat, chemistry, automation, and human skill combine to create a product trusted around the world. And this is where it gets truly extraordinary. Unlike metal pipes, PVC begins with chemistry instead of mining alone. Nearly 57% of PVC comes from ordinary salt, while the remaining 43% comes from hydrocarbons derived from crude oil or natural gas. Salt is mined in countries like China, the United States, India, Germany, and Canada. Meanwhile, petroleum feedstocks arrive from major oil-producing regions across the globe. The journey starts with sodium chloride, common salt. Massive mining machines remove thousands of tons every day from deep underground deposits formed hundreds of millions of years ago. At chemical plants, electrolysis separates the salt into chlorine, hydrogen, and sodium hydroxide using powerful electric currents. What happens next surprised even experienced engineers when PVC chemistry was first developed. At another facility, crude oil or natural gas is refined to produce ethylene gas. Engineers carefully combine chlorine and ethylene to control chemical reactions to produce vinyl chloride monomer, better known as VCM. This colorless gas becomes the essential building block of every PVC product. Without it, there would be no pipes, window frames, or electrical conduits. Next comes polymerization. Inside enormous stainless steel reactors, thousands of tiny vinyl chloride molecules link together into long molecular chains. Temperatures remain around 40 to 70 degrees Celsius, while pressure stays carefully controlled for several hours. By the end of the process, the liquid transforms into fine white PVC resin powder that resembles flour more than plastic. But PVC resin alone isn't enough. Manufacturers blend it with stabilizers, lubricants, impact modifiers, pigments, and processing aids. Every ingredient serves a purpose. Some protect the plastic from ultraviolet sunlight. Others improve strength, while special additives help the molten material flow smoothly through production equipment. The supply chain stretches across oceans. Chemical producers, additive manufacturers, transport companies, and pipe factories work together with incredible precision. A shipment delayed at a port can interrupt pipe production hundreds or even thousands of kilometers away. Most people never imagine that a simple plumbing pipe depends on one of the world's most sophisticated industrial networks. Now the raw ingredients finally arrive at the pipe factory. Mountains of white PVC resin, precisely measured additives, and advanced automation stand ready for the next stage. In only a few minutes, these ordinary powders will become glowing molten plastic, flowing to machinery with incredible force. And that's where the real manufacturing begins. The moment production begins, thousands of kilograms of PVC compound are automatically fed into the hopper of a giant twin-screw extruder. Imagine two massive steel screws rotating together at speeds between 20 and 60 revolutions per minute, slowly pulling the powder deeper into the machine. Friction, compression, and electric heaters work together until material completely changes its form. What started as a cool white powder now becomes a thick, glowing stream of molten plastic. Inside the extruder, temperatures gradually rise from approximately 160 degrees Celsius to 200 degrees Celsius, or 320 degrees Fahrenheit to 392 degrees Fahrenheit, depending on the pipe formulation. Sensors monitor every heating zone with remarkable precision, because PVC can begin to degrade if it overheats. Most people never think about this, But the difference between a perfect pipe and useless scrap can be less than 10 degrees. Workers constantly monitor digital control screens while machinery never stops moving. The molten PVC now reaches the extrusion die, one of the most precisely engineered components in the entire factory. Under pressures that can exceed 200 bar or nearly 2,900 psi, the material squeezes through a perfectly machined circular opening. In just a fraction of a second, the flowing plastic transforms into the familiar shape of a pipe. Watching it emerge feels almost like seeing toothpaste push from a tube, except this tube is creating infrastructure for entire cities. But here's what nobody tells you. The pipe leaving the die remains soft enough to deform under its own weight. Before it can harden, it immediately enters a vacuum calibration tank. Powerful vacuum pumps remove air, while precision calibration sleeves shape the pipe to its exact outside diameter. A difference of only a few tenths of a millimeter could prevent pipes from fitting together correctly. Immediately afterward, the pipe enters long cooling tanks filled with circulating water maintained between 15 degrees Celsius and 25 degrees Celsius. Water sprays continuously across the surface, while the pipe slowly hardens from the outside inward. You hear the rushing water, the steady hum of powerful pumps, and the rhythmic sound of haul-off machines pulling the pipe forward. Every meter must cool evenly to avoid internal stress that could weaken the finished product years later. Next comes the haul-off system. Massive rubber caterpillar belts grip the pipe firmly without crushing it. Servo-controlled motors pull the product forward at speeds ranging from 1 to 20 meters per minute, depending on pipe size and wall thickness. Every movement stays perfectly synchronized with the extruder, because even a slight mismatch could stretch or compress the pipe. Now we reach one of the most satisfying moments in the entire factory. A flying planetary saw races alongside the moving pipe, matching its speed perfectly before making an incredibly clean cut. The spinning blade slices through the hardened plastic in just seconds without interrupting production. What happens next surprised even experienced engineers when they first watched this synchronized system in action. Many plumbing pipes require one expanded end called a socket, allowing another pipe to slide inside during installation. Automated socketing machines heat the pipe end until it softens, then press it into precision molds using hydraulic force. Cooling systems immediately lock the new shape into place. In less than a minute, an ordinary pipe becomes a connection point for entire water distribution systems. Before leaving the production line, every pipe receives permanent markings printed directly onto its surface. High-speed inkjet printers add the manufacturer's name, diameter, pressure rating, production date, and international standard certification. Every printed code creates complete traceability from raw material to finished product. If a pipe is ever inspected years later, its entire manufacturing history can still be identified. At this stage, the pipe already looks complete. It has the perfect shape, smooth finish, and impressive strength. But appearances can be deceiving. Hidden inside could still be microscopic defects invisible to the human eye. That's why the next department uses lasers, artificial intelligence, pressure testing, and experienced inspectors to decide whether every single pipe deserves to reach the customer or be destroyed forever. At first glance, every PVC pipe looks exactly the same. Smooth, white, perfectly round. But here's what nobody tells you. Inside a modern pipe factory, dozens of intelligent inspection systems examine every centimeter long before the product reaches a construction site. Most people never think about this, but a tiny defect smaller than a grain of sand could eventually cause a costly leak underground. The first stop is dimensional inspection. Laser micrometers measure the pipe's outside diameter, wall thickness, and roundness thousands of times every second while the product continues moving down the production line. These instruments achieve tolerances as tight as plus or minus 0.10 millimeters on many products. If measurements drift outside specification, the system alerts operators instantly, and production can stop within seconds. Next comes artificial intelligence. High-speed vision systems capture thousands of images every minute, searching for scratches, bubbles, burn marks, discoloration, cracks, and surface contamination. Advanced software compares every pipe against perfect digital models in real time. What happens next surprised even experienced engineers, because the computers often detect flaws long before human eyes notice them. Appearance alone isn't enough. Engineers also verify the strength hidden inside the plastic. Samples from every production batch enter hydraulic pressure testing machines, where water pressure gradually increases until reaching the product's rated limits. Depending on the pipe classification, testing pressures can exceed 16 bar or more than 230 psi for extended periods without failure. Impact testing reveals another hidden weakness. Heavy steel weights drop onto conditioned pipe samples after they've been cooled to temperatures as low as 0 degrees Celsius, and sometimes even below. The goal is to simulate years of transportation, installation, and harsh weather conditions. A pipe that cracks under controlled testing never reaches a marketplace. And this is where it gets truly extraordinary. Some manufacturers perform long-term hydrostatic pressure tests lasting more than 1,000 hours. Pipes remain under constant internal pressure, while engineers monitor even the slightest deformation. These tests help predict how the product will perform after decades buried underground beneath roads, homes, and entire cities. Every factory also performs chemical resistance tests. Samples spend days submerged in acids, alkalis, fertilizers, and industrial chemicals that the pipes may eventually carry. Scientists carefully measure any change in weight, flexibility, color, or strength. The results determine whether the product can safely serve factories, farms, hospitals, or municipal water systems. Despite all this automation, human experience still matters. Veteran inspectors run their hands across pipe surfaces, listening for subtle sounds and feeling tiny imperfections that machines sometimes overlook. Years of practice have trained their senses to recognize quality almost instantly. Technology provides precision, but skilled people still provide confidence. Only after passing every inspection does the pipe receive final approval. Automated robots stack the finished products into perfectly aligned bundles before wrapping them for shipment. Every bundle carries barcodes and production records that allow complete traceability years into the future. From this point forward, these pipes begin another journey toward construction sites across the world. Now we've seen how chemistry became infrastructure through extraordinary engineering. But one question remains. How many of these pipes does the world actually produce every year? And just how enormous is this industry? The answer is far bigger than almost anyone imagines.